Hello, welcome back. Today we're going to go over an exercise which is going to be the application of the mean value theorem for integrals. So we're trying to come up with the average value of a function. In this case, it's cosine x over the interval 0 and pi over 2. So why don't we go ahead and remember the definition of the average value of a function. As you see that if you have an integrable function f on a closed interval a and b, then the average value of the function is defined as 1 over the distance between the end points times the integral of f from a to b. So at this moment, I want you to remember the mean value theorem and its expression, which is essentially if you start with a continuous function on a closed interval, the integral from a to b of f of x dx is essentially equal to f of c times b minus a. So why don't we divide both sides of the equation by b minus a? So you have b minus a here, integral from a to b f of x dx, and that's equal to f of c. As you see that this integral, which is referred to the average value of a function on the interval ab, is in fact f of c coming out of the statement of the mean value theorem. Here's the average value defined to be 1 over b minus a, the integral of f over the same interval. So for our example, f of x is cosine x, and the lower limit is going to be 0. Upper limit is going to be pi over 2, so this ratio is going to be pi over 2 minus 0. All we're going to do is to evaluate this integral, definite integral, by using the fundamental theorem of calculus. So for that reason, I need to know the antiderivative of the cosine function. In other words, you ask this question to yourself, so whose derivative is cosine x? So for this purpose, you can use the derivative and integral formula card just to see whose derivative is cosine x. It turns out that sine has a derivative of cosine x. For that reason, sine of x is the antiderivative of this function. So all I'm going to do is using the bracket notation. So sine x from 0 to pi over 2. What that means is we're going to evaluate the antiderivative function at the upper limit. So that's sine pi over 2. And subtract. The antiderivative evaluated at 0, which is just sine 0. And at this moment, you can use your TI-84 to evaluate sine pi over 2 and sine 0, or you can use the unit circle. But it turns out that sine pi over 2 is 1, and sine 0 is just 0. So you have 1 minus 0. 1 times 2 over pi is equal to 2 over pi. So in other words, what that means is that the average value of the function cosine x over the interval 0 and pi over 2 is found to be 2 over pi. And here's the graphical outlook of the function cosine x and the average value 2 over pi. So the dashed line is the horizontal line, y equals 2 over pi. And the blue line here is the graph of cosine x. And we are considering the interval 0 and pi over 2. Okay? As you see that the integral, let me just write it to you, the integral from 0 to pi over 2 cosine x dx is the area between the blue curve and the x-axis. Okay? So this whole orange area is what I call to be A. Okay? And the mean value theorem states that this area can be achieved by multiplying b minus a, which is pi over 2, by f of c. Okay, so f of c is in fact the average value. And what is f of c here? Well, we found f of c to be 2 over pi. As you see, this is the height of the rectangle, and pi over 2 is the length of this side here. So essentially, pi over 2 times f of c is the area, this orange area, which is the area of the rectangle. That's exactly the same as this orange area, which is the area between the blue curve and the x-axis. So this tells us that average value of the function over the interval is just 2 over pi. So you can look at this problem geometrically or algebraically. And this problem turns out to be having a lot of applications. Like you can find your average velocity from point A to point B. You can find your average acceleration from point A to point B by using the idea described in this video. All right, that makes the end of the video. I'll see you in another video. Thanks for watching. Bye.